Hi everybody. The code we've been writing for programming assignments has been getting quite long. We know now how to break our main function up into other functions such that one function solves one task with one algorithm. And we know about top-down design, how to write structure charts in order to help us figure out what functions we should write. And we also know about modular programming. So we're learning about how to design code within our files such that it's clean, reusable, readable, maintainable, etc. But all of our code is still in one file, and that file is getting pretty long. Typically, we don't want our files to get very long because if we have a lot of code in one file and maybe we have a lot of different programmers who need to contribute code to that file, it can make maintaining merging code and code conflicts difficult. You also have to scroll a lot and search for code within a file, whereas it would be nice to have code in separate files so you could open them up in parallel, perhaps in two different windows or two different tabs. And that way, your programmers on your team can check out those little individual files and merge them without having any conflicts with other people who are working on those same files, or at least minimize those conflicts. Typically, programs are written such that they are very, very large. For example, think about Microsoft Word, which is a program that most people use all the time. The code for Microsoft Word, I can assure you, is more than a couple thousand lines of code. And it is spread across multiple files because it's such a large program. So there might be folders that contain files that are specifically related to the graphical user interface. Or there might be folders that contain files that are specifically related to how to read and write files to memory, for example. So breaking your code up into different files and even in different folders really helps with organization for large projects. If we head over to today's notes, I've included a link to the Linux source code. You can click at it here. And it'll bring you to a site called GitHub, which is used for hosting source code for open source projects. And you can see this is the source code for the Linux kernel, or the core part of Linux. Our VM is Ubuntu Linux, which is based on this code here. So open source projects are really cool. The fact that you can go see the source code. It's not proprietary and it's not hidden or behind closed doors. So go ahead and just poke around in some of these folders. I'm going to click on the include folder because I want to show you that this folder, Linux include Linux, has over 1,000 files in it. Here's a bunch of folders, so there's even more files in these folders. But look, here are hundreds and hundreds of files. You can just click on one, it doesn't matter. Just poke around in a few of them and you'll see some code that is actually C code. Some of it you'll be able to understand, like for example, here are function prototypes. Here are some pound defines that declare constants. So we use const int, but you could also use pound define to declare your constants. Something that looks like an if else. This stuff is really cool. You can read surprisingly quite a bit of this. After today's lesson, you're going to be able to read a lot more of this code because this file is something called a .h file, which is a header file used in order to make libraries. And we're going to learn how to break our code up such that we make use of .h header files as well. So we'll come back to the Linux source code perhaps later in the semester when we've learned more topics and you'll have a greater appreciation for why the code is broken up into so many files. This is just an insane amount of code. You could not put this all in one file. It would be so long that it would probably take quite a bit of time even to open it off of a disk, a hard disk, into a program if it could even fit at all. So the Linux source code is huge. For organization purposes, the programmers have to make use of splitting their code across different files. So we're going to do that in this video. We're going to organize our code using something I like to call the 3-file format. The 3-file format will break our single .cpp file up into 3 different files, 2 C++ files and 1 header file. Now, typically, as you've seen with the Linux source code, you'll have more than 3 files as part of your program. But since we're just learning to begin to code, we'll start with 3 files, and you'll see throughout your experience in future classes and in side projects and in internships and jobs that the 3-file format is really just a stepping stone to the N file format, where N is however many files that you architect your project to have. Okay, so here's what we're going to do. We're going to break up our reference fun.cpp code into the 3-file format. So let's first make a folder called 3-file format fun, and then make a copy of reference fun.cpp called main.cpp and move it into that 3-file format fun. Typically now we'll put our projects, our code into a folder so that we can keep our 3 files, and any other files, perhaps text files, will be used for input or output together with that code in the folder. Okay, so let's work on this task. Okay, you should now have a copy of reference fun.cpp called main.cpp inside of 3-file format fun. Let's go ahead and open up main.cpp in gedit just to confirm that we do in fact have that code from reference fun. And it looks like we do. Wonderful. All right, so our 3-file format is going to break one large .cpp file up, which in our example is now called main.cpp, into 3 files. The 3 files that we're going to use include a file called main.cpp, which is the driver of our program. The only function that is inside of main.cpp is main. That's it. Main is going to drive the program, meaning it's going to call other functions that are going to execute the bulk of what the program does. Those other functions that main is going to call are going to be in the second .cpp file, which you can name something related to what the functions in that file do. For example, here I'm using GPA computation fun as a coding example to break into the 3-file format. And all of the functions related to GPA computation, I might move into a file called gpa.cpp. So those are the function definitions, which would be in this second .cpp file, gpa.cpp. All of the function prototypes, however, are in neither of the .cpp files. They're instead in a third file called a .h file. So let's keep this all straight. Our 3-file format, we've got 3 files. I've used generic names here. Main.cpp, which contains only the main definition. No other function definitions. Other function definitions are going to be in a second .cpp file. I'm just calling this generically functions.cpp. For GPA computation fun, it might be called gpa.cpp. For our reference fun code that we're going to work with in our example, we might call it dice functions.cpp. Just some examples. Here we'll have all other function definitions. Then in functions.h, this is a header file. We will have all of our pound includes for standard libraries. We'll have our using namespace statements. We'll have our constant global variable definitions. And we'll have all of our function prototypes for the functions in functions.cpp. So typically we name this .h file to be the same name as the .cpp file that contains all of our function definitions. So this is gpa.cpp, this would be gpa.h. If this was dicefunctions.cpp, this would be dicefunctions.h. So to recap, main function definition in main.cpp, all other function definitions in functions.cpp, and then pretty much everything else. The pound includes, the using namespaces, the constant global variable declarations, and all the prototypes for the function definitions that are in here go in the header file. Now, main is likely going to call functions in functions.cpp, but when the compiler encounters a call to a function in functions.cpp, it's got to either have seen the prototype or the definition in order to compile that call. So how does main.cpp essentially access code in functions.cpp? I like to draw this little picture that shows this relationship. So we have main.cpp, and it needs to communicate with functions.cpp. But in order to do so, main.cpp has to go through functions.h. Think of functions.h as the interface between main.cpp and functions.cpp. It's kind of like the middleman, the communicator. So that means that main.cpp has to know about functions.h, and functions.cpp has to know about functions.h. So in addition to the main function definition in main.cpp, we'll have pound include functions.h. One thing to note about this, there's double quotes around the name, and there's a .h here. We've been using libraries that are standard part of C++. Those are surrounded by angle brackets, and there's no .h on the end. But I'm here to tell you that we can pull this all together when I say that we've been including header files this entire semester. For example, pound include IOStream. IOStream is a header file. It's an interface to a library of functions and variables and types related to input-output streams. We are now effectively writing our own libraries. Functions.cpp, or whatever the second C++ file is called, is a library of functions that other programs like main.cpp or some other .cpp file could use. In order to use the code in functions.cpp, all that code has to do is include the interface, include the header file that we write for other C++ files to use our functions. So we're writing our own libraries. That's what header files allow us to do. It's pretty cool. Now, functions.cpp, it needs to also include functions.h. Not because it needs to communicate with main, but because it needs all of these pound includes. It needs using namespace. It needs to use these constant global definitions for variables. So main really needs the prototypes and perhaps some of these namespaces, etc. But functions.cpp, it really needs all of this except for the prototypes. So just to recap, our header file functions.h is like the middleman so that main.cpp can call functions.cpp and functions.cpp can return values to main.cpp. Functions.cpp also needs to use functions.h because it contains information related to the namespaces and the definitions for global variables it might use. And main, depending on how it's structured, may also use like the pound includes in the namespace and the prototypes of functions.h. All right, let's code this up. So we've got main.cpp, but we need a few more files, right? We need dicefunctions.cpp, and we need dicefunctions.h. So we know that main.cpp should only have the main function. All of the other function definitions go in dicefunctions.cpp. So let's go ahead and cut all of those function definitions besides main from main.cpp and paste them in dicefunctions.cpp. Now, the prototypes, the using namespace statements, and the pound includes will be moved into dicefunctions.h so that main.cpp and dicefunctions.cpp can make use of this information without having to introduce redundancy. Now, main.cpp and dicefunctions.cpp won't compile without dicefunctions.h. Main.cpp won't compile without dicefunctions.h because it needs the libraries like fstream. It needs the prototypes for these functions like roll_die. Dicefunctions.cpp won't compile because it also needs the libraries as well as the using namespace standard for utilizing cout, for example, right here. So we need to add one line of code to the top of each of these functions. Pound include dicefunctions.h. Okay, so we have successfully broken up our code for referencefun.cpp into 3 files. We've got communication between main.cpp and functions.cpp via functions.h, which in our particular example is dicefunctions.cpp and dicefunctions.h. So now we're ready to compile our code. However, when we compile our code, we have to compile both .cpp files. So we'll have g++ main.cpp space dicefunctions.cpp. And hopefully all goes well on your end. If you do get an error here, rewatch the video and see what particular portion you missed moving somewhere. But it should work as it has worked here in my code. And I can show those files again real quick here. Running our code works just as before, /a.out, and there's our roll results.txt. So everything works exactly the same as before. Functionally, our code is just the same as when we wrote it in one file with referencefun.cpp. But our code now is much more organized and much more clean and much more capable of being extended into a larger project. If we ever need to perhaps write a program in the future that needs to make use of these functions, we don't have to rewrite them. Instead, we can just add code to our new code that includes dicefunctions.h. And then we can reuse our code just like we've written a library. And just like how we reuse code, for example, in these libraries or in the CMath library. Now, we're almost done talking about the 3-file format. I want to add one more piece of advice or piece of information about header files. You can potentially write code that includes a header file more than once. For example, in this little diagram I've drawn here, suppose we have a file called main.cpp that includes the programmer-defined file header.h, and header.h also includes another programmer-defined header file called top-level header.h. Let's say main also includes top-level header.h. Now, we are from main.cpp double including top-level header.h. This is okay in some cases, but it's not okay in other cases. Let's say that top-level header.h defines a constant integer called pi. Now, when top-level header.h is compiled via main.cpp including header.h, including top-level header.h, that could be the first time the compiler has seen this definition for pi. But then it comes down to the next include where main.cpp directly includes top-level header.h, and it tries to compile that code again, and it sees another definition for pi. It's going to complain and say that you've already declared this variable pi, you can't declare it again. So in these kinds of cases, programmers will put something called guard code in the header file in order to prevent this problem of double inclusion. Guard code essentially checks to see, has this header file already been included? Has it already been seen by the compiler? If it has, then ignore it. Don't include it again. So here's what guard code looks like. At the top of your .h file, you'll have pound if and def, which is short for if not defined, and then the name of some kind of identifier. This is typically called a macro. This can be anything you want, but convention is usually you put this name to be constant macro case for the name of the file. So this is like declaring a constant in some ways. It's a very C-style way of doing it, called a macro. So if the compiler has never included this file before, then, for example, GPA_H will not have been defined. Then it will be defined. Then you put all of your code for your header file here, and then you have your endif, which essentially is ending the block or the body of the if not defined. Then the second time this header file is included, GPA_H will be defined, so this will evaluate to false. And this code in between pound if not defined and pound endif will not be executing, which won't allow for another constant variable of pi to be redeclared. Okay. I'm going to show you an example of why we need header file guard code to help solidify this notion. But before we do, let's go ahead and add our header file guard code to our header file dicefunctions.h. So at the top of our file, we'll have pound if and def dice_functions_h, and then a pound define for the exact same name. These two need to match exactly in order for this to work. And then at the very end of your code, you'll have your pound endif. Every header file you write for this class should have header file guard code because it's good practice, and we are always practicing good practices in this class. So get in the habit of writing header file guard code whenever you're writing a header file. It'll be a little bit different depending on the name of the header file that you're writing it for with these two macros, but over here, the pound if and def, pound define, and pound end diff will always be the same. So this isn't going to change how our program runs because we don't necessarily have any problems of double inclusion here. What I'd like to do now is close out our dice functions.cpp, dice functions.h, and main.cpp, and make a new folder where we'll have an example of double inclusion. I think it'll really help solidify this concept. So we're done with this code. Let's close it. Let's back out of this folder and let's make a new folder called double inclusion. I don't want to put fun on it because it's not necessarily fun. Let's do double inclusion demo. And then let's cd into that folder. We're going to code up this example here. So we'll need a main.cpp, a header.h, and a top level header.h. So in main, we're going to include top level header.h, and we're going to include header.h. That represents these two arrows here coming out of main.cpp. Then in header.h, we need to include top level header.h, representing this arrow right here. And then in top level header.h, it doesn't include any other header files, but we're going to stick with our example and we're going to declare our constant double pi. All right, now when we compile this code, we're going to compile all the .cpp files, which we only have one. So we'll do g++ main.cpp. And we get an error, as we suspected, because I told you there would be an error. And it says top level header.h, line 3, error, redefinition of const double pi. Okay, this is really cool, right? We're seeing that if we include a header file twice, then without guard code, we're going to get an error as the compiler is saying, I've already declared a variable that looks like this. You can't declare another one. And then if you look slightly above here, you can also see kind of the path or the trace of how the code even got to top level header.h. It says in file included from header.h from main.cpp line 2. So line 2 is header.h. Then we go to header.h and it says line 1. Here's line 1. That's how we're getting to top level header.h the second time. If we were to change this order, this would look slightly different. Before, we were getting to top level header.h via header.h, and now it just says in file included from main.cpp line 2. So the second time now we're seeing the declaration of pi is from top level header.h directly, whereas before it was indirectly via header.h. Okay, so let's fix this. we can go ahead and add our header file guard code to fix the problem of double inclusion. Now we go to compile our code, and it compiles. So you can really see now how header file guard code guards or protects against double inclusion, which can cause errors like this one where we try to redefine a variable. Now, even though our code compiles, we should head over and add the guard code for header.h because we really don't know how our code will be used in the future. We may foresee that header.h will never be included twice by some other code, but we can't foresee that. So we always want to write our code to be as robust as possible because we just don't know what other programmers or even ourselves in the future are going to end up doing. And it still compiles no problem. All right, so 3-file format, incredibly helpful for organizing our code and breaking up such that we don't have these really long C++ files. The 3-file format is a stepping stone to architecting large software projects where you have multiple files. If you get the chance, just head over to GitHub and search for some other projects. Maybe in the search box, just type in something you're interested in, and you can see how large software projects usually are. There'll typically be multiple directories, and in those directories, multiple other directories, multiple C++ files and header files, or maybe you're looking at a different programming language like Java. There'll be a lot of different .java files, for example. So definitely poke around on GitHub, and you'll get a sense for more of an appreciation for the 3-file format.